Okay, let's start. So what is backtracking? Backtracking is one of the most powerful algorithm design techniques that is also based on recursion. Where do we use backtracking? You can also think of, say, DFS and BFS as some kind of backtracking. Once we reach a dead end, we backtrack, right? We have used these words in real life. Think about if you're lost in a maze, what do? Whenever you hit a dead end in a maze or a cave, what do? You backtrack. You backtrack and come to that node from which you can take another direction, a deviation. That's it. That's the high level idea, right? Backtrack, we use it in real life. So here we formalize it and use this technique for solving a lot of problems. What kind of problems? So here we will majorly target combinatorial problems. What do you mean by combinatorial? In mathematics, you might have heard about combinatorial objects, right? So what are those? Permutations, subsets, compositions, partitions, Catalan numbers, Diophantine equations, solutions, right? N queens. So there are hundreds and hundreds of these combinatorial problems. The number of shortest paths or the number of paths from one point to another point in a graph, the number of minimum spanning trees or the number of spanning trees, all these are combinatorial problems, right? The number of such combinatorial objects itself typically is exponential. And now think about permutations. How many permutations are there? N factorial. So there are n factorial permutations. Okay, let me write that. So this is an important point, right? N factorial permutations. So n factorial, is not polynomial time, right? So is it possible to ever come up with a polynomial time algorithm to generate all permutations? No, impossible, right? This is impossible because the number of objects itself is n factorial. The output size itself is minimum n factorial. It's okay. Each permutation, right? There are n factorial permutations, but each permutation is of size n. Even if you assume you're not counting the permutation size of one permutation, the number of permutations itself is n factorial. So for some of these problems, it is impossible to come up with polynomial time algorithms. You can have a polynomial time algorithm to compute the number of permutations, but not generating all permutations. See the difference? One is counting. Counting is easy. You can apply a formula. But generation is you need to visit every object. You cannot do that in, right? Polynomial time, right? N factorial. Similarly, subsets. How many subsets are there? 2 power n subsets. Let's assume for simplicity all elements are distinct. Then 2 power n subsets. So can you come up with a polynomial time algorithm? No. So for all these generation of combinatorial objects, right? So the best possible way to solve these problems, or you can also say the standard way to solve these problems is using backtracking. And we will see examples. Okay, backtracking. For some of these problems, there may be a better algorithms. Now think about it. Suppose you want to now think about knapsack problem. Knapsack, okay. In the knapsack problem, the brute force way to solve the knapsack problem was generation of subsets, right? Generation of subsets. But does that mean that there is no other algorithm that does not use the concept of subsets? No, right? So we saw dynamic programming way to solve the problem that automatically includes subsets in that DP table, right? We didn't have to create all these 2 power n subsets. And there is another one fantastic problem. You might have heard about this bridge crossing puzzle. So there are 4 people, right? You can generalize this. Suppose there are n people, right? N people with say time 1, time 2, so on up till time 3. Time n. So they want to cross a bridge, okay, at night. So person 1 takes T1 amount of time to cross the bridge. Person 2 takes T2 amount of time to cross the bridge, and so on, right? So all these friends, n friends, have to cross the bridge here. However, the capacity of the bridge is, say, C. For some C less than or equal to n. That means all people cannot cross the bridge simultaneously. At most, C people can cross the bridge. Okay, next. So it is night. So they have the torch, right, to cross the bridge. So when a set of at most C people cross the bridge like this, one of them has to return to get the torch, right? You have to transfer the torch back. And again, the another set can cross from left to right. Now, you want to find what is the sequence of crossings and what is the minimum time taken to cross the bridge for these n people with all these times T1 to Tn and given C as the capacity. So this is one very famous Microsoft interview problem. I mean, they won't give the numbers as n and C, they give the numbers as 4, and maybe these are 1, 2, 5, 10, right? What is the best way to solve the problem if the capacity is 2, right? So you try to solve this problem. So if you solve it using backtracking, you get an exponential time algorithm, right? Exponential time algorithm. You can also solve it using backtracking. So finding multiple subsets and computing related to that. However, there is a very powerful dynamic programming solution to solve this problem. Extremely powerful. And it is super complicated. That can solve the problem in n squared time. So that's the power of algorithmics, right? So some problems you might think that there is no other way to solve it except that standard or brute force approach. But, right, if you think really, really hard, maybe, right, there is a better algorithm. But here, the question itself did not say that you have to make use of subsets. The standard approach makes use of subsets, hence it was exponential time. But here, permutations, subsets. The question itself says generate all permutations, generate all subsets. So there cannot be any polynomial time algorithm to solve these problems, right? So this is a different instance. Knapsack is a different instance, but these are different instances, right? Different problems. So depending on the problems, the how it is asked, how it is posed and everything, there may or may not be polynomial time algorithms, okay? Anyway, so right now we will focus on pure backtracking, not, if there are more efficient algorithms than backtracking, okay? So I think we will cover permutations, subsets, Diophantine equation, and n-Queen's problem, right? Hopefully we will have time to cover all this. Let's start. So here is your backtracking framework. So what do I mean by a framework? Hundreds of backtracking algorithms have this template. I cannot claim that all backtracking algorithms will adhere to this framework, but as per our analysis, right? So we have tried this for at least 40 problems, and we see that it clearly follows, all the backtracking algorithms for 40 plus problems, right, adhere to this template or this framework. Okay, so this is a very powerful framework. You may or may not find this exact framework in books, right? So they will loosely give you the ideas, but here is the rigorous setting of it. Okay, now let's try to analyze what's happening. So backtrack is the algorithm, right? And depth, you have something called depth. Okay, we will try to understand this later. Then it's like this. When you run this backtrack function, you are going to touch every node in this recursion tree. And you have seen recursion trees, right? Every recursive algorithm will have a recursion tree. Backtracking will also have a recursion tree. Okay, so what do you mean by depth? Depth, you can assume it is this. Here depth is equal to 1. Here depth is equal to, say, 6, right? The distance from the root. Okay, so that is depth. If reject of depth, then return. That means you found a condition such that that instance will be rejected, then you return. Okay, we will understand this when we encounter different problems. So if it is the reject condition, we return. That means we backtrack. This is backtrack. Suppose we encountered one node, right? Node, and the conditions satisfied this reject constraint. Then we return. What do you mean by return? We go to its parent. We go to the caller of this node. And that is the meaning of backtrack, right? Okay, if accept, then output. So if it is the accept condition, we output. What do we output? It might be combinatorial object. We will just give this depth, and probably we will print the combinatorial object or something. Assume that all other combinatorial objects and many other variables are global variables. Okay, so we have not shown all those things here. So I have shown only the depth, because depth will keep changing, but assume that other objects, combinatorial objects, and all other things are global variables or accessible from the class or whatever. Okay, so this is the reject condition. This is the accept condition. Then what do you do? Else, you have a loop. There is a loop. There is an I loop. Okay, so based on some function of depth. And for each iteration of this loop, you check some constraints, right? If it is true, then what do? You allocate some resources, recursively call the backtrack function for depth plus 1, and deallocate resources. Okay, let's try to understand this in a different way. Suppose this is your combinatorial object. Assume that your combinatorial object is an array, right? Because permutation is an array. Subsets is an array. Solutions to Diophantine equation can be considered as an array. And what else? So on. So any combinatorial object, assume that for simplicity, it is an array. Now you are trying to compute the value for depth, right? That means if depth is equal to 1, you will fill this. If depth is equal to 2, you will fill this. If depth is equal to 3, you will fill this. Suppose you are currently here. depth is equal to 4. You want to fill this cell of the combinatorial object. Maybe the fourth value in the permutation or the fourth value in that subset, and whatever it might be. Okay, so reject condition, accept condition, and then the loop. That means the value that is taken here will be in a range that can be the first value, second value, third value, fourth value, whatever. So there is a loop of values for depth. So there is a loop of values. Some of them satisfy the constraint. Some of these values do not satisfy the constraint. You will try each and everything, right? So this did not satisfy the constraint, so do not worry about it. Okay, this did not satisfy the constraint, do not worry about it. Okay, this satisfied the constraint, this particular value. What do? You allocate resources, right? Maybe you say that, okay, so this was say 10, I'm allocating 10 here, right? So it can be reducing the count, it can be assigning the value. This allocate resources has a deep meaning. Okay, do not worry about understanding everything right now, but you allocate resources, then you backtrack. What do you mean by backtrack? So you have set the value here, right? Backtrack of depth plus 1, you go here. Now depth plus 1 is equal to 5, right? So on, you keep continuing. Suppose you return back at some point in time. So what do you do here? Deallocate resources. Once you're done with this, you deallocate resources. You remove 10 and maybe 17 is the next value, right? You will substitute 17, again call backtrack of depth plus 1 and continue. That means for each cell, let me erase this and rewrite this. See, this is depth. For depth, there are multiple values that can take, right, in this loop. Some of them satisfy the constraint. So you try each of these values that satisfy the constraint and then recursive and call the backtrack function for the next cell. So you keep doing it. So that means you will try for all possible combinations for the first cell, all possible combinations for the second cell, and so on up till the last cell. Make sense? So this is how you are running an exponential time algorithm. And typically it will be exponential almost always, right? I mean, there can be exceptions, but typically, because you are trying all possible values at every cell of the combinatorial object, right, that satisfies the constraints, right? So you are covering all permutations or all subsets and so on, right? So now let's see an example. So this is your framework. Remember this framework. We will use this format everywhere for every problem we will see, okay? Permutations. Okay, so here is your problem. You are given a set of items, item of 1 to u, item of 1 to u. These are unique elements. Okay, and item 1 can appear count 1 number of times. Item 2 can appear count 2 number of times. Item I can appear or can repeat or can occur count I number of times. So those are the number of instances of that element that you can use. Okay, now, right, the total number of items will be count of 1 plus count of 2 plus count of 3, so on up till count of u. Okay, this is clear, right? N is equal to this. Now let's take an example. R is equal to 3. So what is R? We want to generate R permutations. You know what is R permutations, right? If there are 100 objects, if you want to generate, say, 4 permutations, that means you just need permutations of size 4. So this is much more generic definition than normal permutations you have seen, right? So this is a much more generic problem. So the algorithm I'll be giving here is more generic than most algorithms you will see in books. The reason is this algorithm works for duplicates. This algorithm works for R permutations. Many algorithms do not work for R permutations. And many permutation algorithms given in books do not work for repeated elements. Right? The one we will cover here is so powerful and so generic, right? When you implement and compare it with textbook algorithms, you will see the power of this. Okay. Then the 3 permutations, okay, now R is equal to 3. Okay, we want 3 permutations. U is equal to 2. That means unique items are 2. And those items are A, B. I mean, you could have chosen 1, 2, A, B, whatever you want, right? Alpha, beta, whatever you want. Count is equal to 2, 2. That means there are 2 instances of A. There are 2 instances of B. Now then the 3 permutations of AABB. So how did you get AABB? Because there are 2 instances of A, AA. There are 2 instances of B. So you have AABB. The 3 permutations of this are AAB, ABA, ABB, BAA, BAB, BB. So here, when you select a B, it doesn't matter whether you have selected this B or this B. I mean, they are not numbered Bs, right? Any B is the same here. So AAB occurs only once, right? Similarly, ABA occurs only once. The size of each of these is 3. That's why these are called 3 permutations. The constraint is that you cannot use A more than 2 times. You cannot use B more than 2 times. Make sense? This is our problem. We want to generate R permutations given a set of unique elements and given the count array. Count array is the number of instances you can use. And why do we typically use count arrays? Think about in, say, operating system. Maybe you have 5 instances of a printer. Maybe 4 instances of some server, right? So that is the count array. Make sense? Okay. Now let's try to see the algorithm. This is the algorithm. We will understand the algorithm using the recursion tree, but let's see the pseudocode first. Permutations of depth. So this is the local variable depth, and others are global variables, right? So I didn't add all these variables because it can be confusing. Hence, all these are global variables. R is a global variable. Combinatorial object R of 1 to R. So what do you mean by this? You're generating all R permutations. You know, R permutations are of size R, and we call that variable as, say, R. So whenever we generate this, we print it or visit it or use it or process it. Okay, assume that we will just process it. We don't need to store it in a big array, right? We don't need to store it, because space is very important, right? Typically, whenever you deal with backtracking algorithms, you don't store it. So here I have just said print, but in real life, you can replace this print with process, right? Process or execute or, visit. Okay, it won't be printing. It will be processing. For example, permutations. Suppose you have 100 different tasks or features that you want to test. You can take the permutations of those features. You change the orders, right? Order of those, features or function calls or whatever, and you are checking or testing whether they are working properly. Then you don't print all that orders, right? You just process it. You run those features and check whether it is working or not. So that's the meaning of processing here. So though we will use printing everywhere, but it really means processing. Okay. Next, unique items u, item of 1 to u, occurrences, right? Number of instances. So generate all R size permutations. We will store it in R of 1 to R, dot, dot, dot. Okay. The first call to this is permutations of 1. Depth is 1. So as I said, it's a recursion tree and depth starts from 1. Now, here is the code. Look at this. If depth is greater than R, then print R of 1 to depth minus 1. That means here is your recursion tree. So this was 1 and this was R. So this is R plus 1. When the depth is R plus 1, what happens? Depth is greater than R means depth is R plus 1. What happens? You went to a level that is greater than R. This is where you need to stop, right? You need to output. This is the except condition, except condition. Except, what do you need to accept? That means print or visit process. R of 1 to depth minus 1. Depth is R plus 1, so this is 1 to R. So that means you will print the combinatorial object here. Right? That's the meaning of except condition. This is the except condition. Else what do you do? For I is equal to 1 to u, if count of I greater than or equal to 1, R of depth is item of I, count of I minus minus. Okay, what's happening here? Now let's take a look at one node, any node, right? Any node in the recursion tree. So what do you mean by this? There are u number of child nodes. See, u number of child nodes, because in every child node you will be calling this permutations of depth plus 1, right? So there are u number of child functions. Okay, if count of I is greater than or equal to 1, suppose your items are say A, B, C, D, right? So like what do you do here? For I is equal to 1 to u, if count of I is greater than or equal to 1, that means if count of this, that means the number of instances of A is at least 1. If it is at least 1, what do you do? Add this item of I. So add A. So suppose you want to add at this cell, right? R of depth. So you're computing this cell, R of depth. See, R of depth. At depth. How do you compute? The branch factor is at most u. For each of these items, you check whether the number of instances of A is greater than or equal to 1. If it is, you try A here, right? R of depth is equal to item of I, that means A here, and count minus minus. You already used 1A, right? You decrease the count of A and again recurs. That means you go in the future. R of next you will try to assign R of depth plus 1, so on. Similarly, so once you come back, right, in the next iteration of the loop, you will try B. You will try B. I is equal to 2, right? I is equal to 1, I is equal to 2, I is equal to 3, I is equal to say 4. And this is item of 1, item of 2, item of 3, item of 4. And then the count will be decreasing whenever you add this. So on. So the branch factor is at most u. Why at most u, not exactly u? Because depending on this constraint, it may or may not call the function. Right? It may or may not call the function. So it is at most u. Make sense? So this is the high level idea. Let's see an example. Okay, let's start with this. So we are starting with this. Item is equal to AB. Count is 2, 2. We want 3 permutations. So initially assume that everything is null. I mean, nothing is added in this combinatorial object. And you call permutations of 1. That's how you invoke the algorithm. Okay. So then what happens? You have a loop. What is the loop for? That loop is I is equal to 1 to u, right? I is equal to 1 to u. So here u is 2, so I is equal to 1 to 2. So the branch factor is at most 2. So that's why you see the branch factor is at most 2. So what do you do here in at most 2? So when I is equal to 1, you try to add A into the first position. When I is equal to 2, you try to add B in the first position. See, here depth is equal to 1, right? See, in all these things, look at this, depth is 1. Depth is 1. In all these nodes, depth is 2. In all these nodes, depth is 3. Okay. Whenever depth is equal to 1, you try to assign the first element of the combinatorial object. Whenever depth is 2, you try to assign the second position of the combinatorial object. Whenever depth is 3, you try to assign the third element of the combinatorial object. Whenever depth is 4, right? 4 is greater than 3, because R was 3. 4 is greater than 3. You stop, you accept, you print or process. That's it. And return to the caller. Make sense? So that's the meaning of depth here. So depth, you can assume that it's the depth of the recursion tree. At the same time, it is the index at which the index of the combinatorial object where you will be assigning values. Okay, so when you assigned A here, count of A decreased by 1. When you assign B here, count of B decreased by 1. Correct? Next. And then you recursively call with depth is equal to 2. So either A, right? There are, again, the branch factor is at most 2 here, right? You assign A or you assign B here. It is this. If you assign A, the count of A decreases by 1. If you assign B, the count of B decreases by 1. Make sense? Similarly, if you assign A here, B here, the count decreases by 1, respectively, of A and B. And similarly, what happens here? Now, this is an interesting case. Now, depth is equal to 3. Depth is equal to 3 here. We have I is equal to 1 and I is equal to 2. We can assign A or B here, right? Okay, we check if we can assign A. What happens? What happens? Count of A is 0. That means there are no instances of A that you can use. You are running out of all A's. There are no more instances of A's that you can use. So if A is a printer, the number of copies of printer was 2, you have exhausted all those copies of that printer, right? So you cannot use I is equal to 1 or assign A for the third position. So this will not work, right? I mean, there won't be a function call at all. So there will be a function call only with respect to B here. You can assign B at the third position, and the count of 2 can be decreased by 1. And as this is non-zero, you can assign one instance of it, and decrease the instance by 1. See, if the count is 0 anywhere, you cannot assign that object. That is the meaning of constraint here. The loop is related to the branch factor. Loop is related to the branch factor, or the number of child nodes. The constraint is related to reducing the branch factor. Reducing the branch factor. So here the branch factor was 2 everywhere, right? Loop, because I is a loop from 1 to U. U is the branch factor. But constraint says that only if the count value is greater than or equal to 1, that means there is at least one instance of count, only then assign that particular object or printer or whatever. So that will decrease the branch factor from U to something less than U. So here the branch factor was 2 in general at most, but here in this case, at this particular node, it's no longer 2, it's just 1. Right? So here also, it's no longer 2, it's just 1. There is only one child node. Make sense? At the end, what happens? If you keep continuing, depth will be 4 at some point, and 4 is greater than R, that is 3. And there is no fourth position or index in the combinatorial object, right? So you don't want to assign anything there. You just need to stop. So print or visit that combinatorial object and return. Return where? Return to the caller, right? Whoever called that function, return. If you don't do anything, right, it will just return. Make sense? So any questions here? This is very important, right? The permutation algorithm shown here is way more powerful than the other algorithms covered in many textbooks. And the reason is this works with duplicate elements, and this generalizes to R permutations, not just complete, full permutation and permutations. So this is much more generic. If you said R is equal to N, you get all N factorial permutations, assuming N is unique. But if there are duplicates, many other algorithms do not work with duplicates. Make sense? Hence, this is the beautiful framework, right? This framework, whatever we've shown here, is a very powerful framework. You can come up with very generalized algorithms. Questions here? Questions? Questions?
It's a lot to take in at once.
Yes, yes. This is hard, right? There are so many ideas here. Count, combinatorial object, depth, I, loop, constraint, right? Yeah, so, but you got the rough idea how the recursion unfolds, and what is the branch factor, and what is the constraint, right? See, understanding branch factor is very important. How you get options for every position, and understanding constraint is very important. So top 2. Later, okay, you can understanding allocating resources, How did we allocate resources here? Right? Allocating resource just means assigning these values at those particular positions and then decrementing the number of instances of that object. That's the meaning of allocating resources. And like when you go back, you deallocate resources. See, when you go from here to here, or say here to here, you deallocate resources. You can remove this, right? B, and from you can increment the count. Right? I mean, that will happen automatically. Okay. Right. Now let's move to subsets. Probably I will skip Diophantine equation. So after this, we will cover n-queens problem. Now let's look at subsets. Subsets is also one very powerful combinatorial object. It occurs everywhere. You might have heard about binomial coefficient, right? We discuss in detail about binomial coefficients. And binomial coefficients are related to combinations, permutations and combinations. What is combination? There are n objects, you want to choose R objects. In how many ways can you choose R objects? When you say you want to choose R objects, you cannot order them. You cannot rearrange them like in permutations, right? It's like a set. It's not a sequence. Sequence has ordering, permutation has ordering, tuple has ordering, array has ordering. A set has no ordering. A combination has no ordering, right? It's unordered. Make sense? Okay. Now you want to generate also. So, another point I wanted to make. Now think about the equivalence between subsets and let me think about this. So you have a set with, let's say A is a set with n elements, right? A is a set with n elements. The power set of A has 2 power n elements. What do you mean by 2 power n? The set of all subsets of A will have 2 power n elements. That means the number of subsets of A are 2 power n. Now compare it with n-sized binary strings. Binary strings. How many n-sized binary strings are possible? 2 power n, right? 0 or 1 for the first bit, 0 or 1 for the second bit, so on up till n bits. So 2 power n possibilities. So is there a relationship between subsets and n-sized binary strings? Yes. Right? Suppose there you consider n is equal to 4. Consider A, B, C, D. And you want to take the subset B and C. So that can be represented as 0, 1, 1, 0. A is not present, hence you give 0 to A. B is present, you give 1 to B. C is present, you give 1 to C. And D is not present, hence you give 0 to D. So bit strings and subsets are related. Okay, so similarly combinations and subsets are related. Okay, let's come back to the question. So generate all subsets of U unique elements, item of 1 to U using count array, same as before. You have instances, item is equal to ABC, count is equal to 1 to 1. You want to generate all subsets here. Okay, all subsets of this. I mean, we have other algorithms also where you want to generate R size subsets and all, but we will not look at it, right? So this is one of the backtracking. There are many more. These are the subsets. Okay, now let's go to the code. So here is your pseudocode. So remember the framework. You have the backtrack function, and here you print. And here you reject. So this is the accept constraint. This is the reject constraint. What do you mean by accept constraint? So whenever you come here, you are accepting that particular object. So if you hit this constraint, you will reject it. Okay, that means you will reject it. That means trace back trace. Okay, then you have a loop I is equal to 1 to u, and we have some complicated expression here. Count of I greater than or equal to 1, depth is equal to 1, or item of I greater than or equal to r of depth minus 1, so on. And these lines are exactly similar as in permutations, right? Line 6, 7, 8, 9. You assign the element to r of depth, you count the number of instances, right? As you use one of these, you decrement one instance of that item of I, and you recursively call subsets and increment it to fix it. Okay. Now, the most complicated thing here is we want to understand why do we have line 1, line 2, lines 4 to 5, 4 and 5. So other things, right, 6 to 9 automatically derive from permutations, right? It's very similar to permutations. Okay, so if you look at it, the template looks really the same, right? Really the same. Okay, now let's see the example, and maybe we will come back to this after this example. Now look at what's happening here. Item is ABC, count is 1 to 1. You have the R combinatorial object, that is the subsets. And what is the difference between this recursion tree and the recursion tree of permutations? So here, every node is an accept node. Look at the colors. Blue means you are printing it, you're visiting the object or printing the object. In permutations, you are printing only at the dead end, that is the leaves. So here you are printing every node. You're processing every node. So every node is a subset here. Let's see if there is a pattern. What is the pattern? Look at the pattern. The first element is A, the first element is B, the first element is C. Given that the first element is A, the second element is B, the second element is C. Given that the second element is B, the third element is B, third element is C. Make sense? Given that the third element is B, the fourth element is C. And similarly, what do we have here? Given that the first element is B, the second element can be B or C. Given that the second element is B, the third element has to be C. So let's understand this tree, right, in some depth. If you analyze the entries in every combinatorial object, you see that you have a couple of characters and they are in increasing order. BBC, A, B, B, C. You don't see a subset as B, B, A. Can you tell me why? Why? See, in subsets and combinations, order does not matter. If you want to discourage ordering, if you don't want ordering, if you don't want arrangements, then what do you do? You have to strictly follow a particular ordering, one particular ordering, so that, right, the permutation won't happen. And how do you fix this ordering? You can say that whenever you have added one character, right here, one element, the next element has to be greater than or equal to the previous element. Correct? So if this is the previous element, the next element you add here will be greater than or equal to the previous element. See, B is greater than or equal to A, C is greater than or equal to A, B is greater than or equal to B, so on. Right? So this is one very important property. Whenever you have an element, the next element you add is greater than or equal to the previous element or value. When I say greater than or equal to, it can be alphabetically greater, numerically greater, whatever. I mean, but there should be some ordering. Okay, fine. So that is one important thing. Second, so you can think about this common prefix. Look at this. AB and AC have the common prefix A. ABB and ABC have the common prefix AB. So the way this is working, right, the way this recursion tree is built is like this. You try all possible combinations for the first character. Assuming that the first character is fixed or first item is fixed, you try all possible combinations for the second item, second character, second position in the combinatorial object. Here, for the first character, it's ABC, right? Easy to see. If you add A, the count of A decreases by 1. If you add B, count of B decreases by 1. If you add C, count of C decreases by 1. Okay, once you have added A, now you can try adding ABC for the second position. Can you add A to the second position? No, you cannot. The reason is count of A is 0. That means currently there are no instances of A that you can use. The max number of instances of A you can use was 1, and you have already used all A's, all those instances. No more reuse of A is allowed. So AA is impossible. So another constraint is you need to make sure count of I is greater than or equal to 1, right? The number of instances should be at least 1, else you cannot use it, assign it. This is another important constraint. I mean, very similar to permutations also, right? We had this in permutations. So you cannot have, this is the branch for A, branch for B, branch for C. A is not possible. What about B? B is possible. If you add B, you will decrement the count of B by 1, right? 2 to 1. If you add C, you can decrement the count of C to 0. Similarly, okay, this was anyway not possible. Now let's try this node. Let's have ABC from here. ABC, ABC. A, B, C. Can you add A? You cannot, because 0 instances of A. Can you add B? Yes, you can. Can you add C? Yes, you can. Right? Got this. Now, so try from any node like this, right? Continue the same idea. A, B, C, A, B, C, A, B, C. Can you add A? No. 0 instances of A. You cannot add A. Can you add B? No, there are no instances of B left. No. Can you add C? Yes, I can, because there is 1 instance of C that I can add. Add C, and the number of instances of C will also decrease to 0. At this point, what happens? Again, so if you go to the next level, right? Next level, what happens? Depth is equal to 5. You cannot add anything. It will automatically return, right? Or if depth is greater than the total number of the max size of the subset, then also it will return. Okay. Now here, I mean, continuing in the same manner, right? You can apply the same logic for every node. Let's apply it for, say, this node here. So here, suppose you have A, B, C. For the next character, you want to add A. Can you add A? So tell me, can you add A here for the next character? BCA. BCA is not possible because our first constraint was the character you add later must be greater than or equal to the previous character, the last character, right? So A is not greater than or equal to C. Though the count is there, the number of instances of A is 1. You could have added A, but we are dealing with subsets. In subset, we don't want duplicates. See, A, B, C has been added already. We don't want to again repeat BCA. BCA is the same set as ABC, right? So we cannot add A, not because there is no instance of A, there is. However, A cannot appear after C. What about B? Can we add B? No, because B cannot appear after C. What about C? C can appear after C because C is greater than or equal to C. However, the number of instances of C is 0. Hence, we cannot add C. We don't have one more copy of C to be added. Hence, we cannot add C. Make sense? So in some cases, we had the count, but the order was messed up, so we cannot add those characters. In some other cases, we didn't have the count, but order was proper, but we didn't have the count or instances, hence we cannot add. So both these constraints are important. Make sense? So does this make sense? See, once it exhausts all these possibilities, it has to return to the parent here, right? And once it returns to the parent, it will deallocate the resources and it will return to its parent. So does this make sense? Okay, now let's go back to the code here. See, this might take some time to understand, right? Because backtracking algorithms in general are complicated to understand. You will need to extensively use recursive diagrams, recursion trees to really understand it. So try to go over each and every node there Or another idea you can do is try debugging, right? Look at the control, try to create diagrams of recursion trees. So then you will understand, okay, what's actually happening, why it's happening, and you can print out the state variables, right? You can see, call these are as the state variables. What is the depth value? What is the count? What is the R value? And so on, right? So with these state variables and debugging, you can try to understand how exactly this is working. Because recursion in general, right, it's difficult to understand. Okay, so as we said, every node is an except node. Every node is an except node. If depth is greater than n, then we will definitely return, right? We are done with this, we will definitely return. Okay, in other cases, we will try all possible values from 1 to u. As I said, in the example, we will try A, B, C, right? Item of 1, item of 2, item of 3, that is A, B, C. We tried everything. However, this constraint is important. So what does this constraint mean? You need to make sure that the number of instances is at least 1. If there is no instance, how can you add that element, right? You need to have at least 1 instance. Else you cannot add that element at all, right? Okay. So another constraint is this. Make sure the item that you are adding, the current item is item of I. The current item that you want to add in the next character of the combinatorial object is greater than or equal to the previously added character to the combinatorial object. What is the previously added object? R of depth minus 1. Because the current iteration is on depth, you're trying to add for a value for R of depth. You're dealing with this cell now, R of depth, right? So you check the current item that you are dealing with, whether it is greater than or equal to the previous value or the previous character of the combinatorial object, R of depth minus 1. If it is, then you can go ahead and add, right? If depth is equal to 1, you don't need to worry, right? Because there is no previous object here. There is no R of, see, if depth is equal to 1, you're adding something at R of 1. You don't need to worry about R of 0 because R of 0 does not exist as per our definition. So if depth is equal to 1, you can still add, or if depth is greater than 1, then you need to check if the previous value, right, is less than or equal to the current value item, or item is greater than or equal to the previous value. Only then you can add the item, the current item to the R of depth, right? And decrement the count of it, recursively call it. Once you are done with all this, right, increment the count. That means you will update the count. See, once you're done with printing it all, right? See, you initially decrease the number of printers, right? The instances of printers. So once you're done with all the jobs, what do? You release the printer to the printer pool. So count of I++. So that's the meaning of deallocating resources and allocating resources. These are, kind of inverse operations. Make sense? So any questions here? Questions? See, it will take time to understand this code, right? There are so many constraints here, but try to go over this diagram and how exactly the count values are reduced, depth values are changing, and so on. See, this is depth 1, hence you are adding the first character. This is depth 2, you're adding the second character, third character, fourth character, so on. And here the branch factor is 3, no problem. Branch factor, right? The first one does not work. Why? Similarly, so here there can be, so try to write these branch factor 3 at every node and see why some are neglected. Then you will really understand, okay, what are those constraints that will make sure that those child functions are not caught. See, here also the branch factor was 3 before, right? And due to some constraints, none of these executed. Due to some constraints, none of these executed. Why? So you need to do this debugging and trying to go deeper in this recursion trees. Okay, you'll understand the algorithm better. So we'll skip all this. Let's directly go to n queens problem. This is a very famous problem. So what is the n queens problem? You are given an n cross n chessboard, and here no two queens fight, right? You want to place n queens on an n cross n chessboard such that no two queens fight. What do you mean by fight? Two queens cannot be in the same row, right? Then they attack each other. Two queens cannot be in the same column. Then they attack each other. They cannot be in the same diagonal. It can be left diagonal or right diagonal. So you cannot have something like this. Two queens in the same row, same column, same left diagonal, same right diagonal. This is not allowed. Right? So with these constraints, you need to place n queens on n cross n chessboard. So how does this work? Let's think about it. So 1 cross 1 chessboard, you can place one queen. 2 cross 2 chessboard. Suppose you place a queen, you cannot place another queen here. You cannot place another queen here. You cannot place another queen here. So for 2 cross 2 board, it's impossible. There is no solution. What about 3 cross 3? Is there a solution for this? Think about this.
No, no solution.
No solution. Why?
Because if 2 has no solution, 3 has no solution.
Okay, if 3 has no solution, 4 has no solution?
No, 4 is different because you know, the word beginning, right? So I mean, as long as you left the 1, you have to place this into a let's consider this, right? If you look at the 3, right? The top left, the very top left has to can be occupied. Then you go to the rest of them go to the 2 by 2. That's why it cannot.
Good.
Yeah,
Okay,
cannot
so
solve
try
it.
this, right? So try 3, 4, everyone, 3, 4, 5. So you can try this. So one is check whether it is possible or not. Second is try to find how many ways you can place, right? The number of such solutions, if solutions do exist. Okay, so this is one thing. Fine. So how do we represent the output? You can give a diagram, that's fine, but we want, if possible, a succinct representation. So consider n is equal to 4. Now let's look at n is equal to 4. So here is a succinct representation, 2, 4, 1, 3. So this is row 1, row 2, row 3, row 4. So 2 means second column in the first row, fourth column in the second row, first column in the third row, third column in the fourth row, right? So 2, 4, 1, 3. Does this work? No two queens attack each other here, right? They are not in the same row, same column, same left diagonal, same right diagonal. What about 3, 1, 4, 2? 3, 1, 4, 2. This is also a solution. This is also a solution, right? So similarly, for given arbitrary n, can you place n queens on n cross n chessboard, right? To satisfy all these constraints. So that's the goal. And this will be the representation of the output we will follow. This is succinct, right? We don't need to, have a 2D array or something like that. So in 1D array, we can encode one solution. Yes.
Actually, this is a symmetry, right? So you just turn around. I mean, it's reflection for kind of mirror.
Correct. So there can be reflections. So here we are interested in just one solution, but you can generalize and get all solutions. And you can also add one more constraint, that it should be rotationally invariant, right? But that will slightly complicate things, but those are doable.
Okay.
So here we don't need to care about rotation invariance. So try to get every possible solution, even if, right, they are same with respect to rotations.
Now we're looking for just one solution.
So let's see how this has been coded. All solutions.
All solutions. Okay.
Yes.
Yeah,
All solutions.
okay.
We are trying to get all solutions. Right?
Yeah.
Okay. I mean, we can add further logic to make sure these are rotationally invariant, but currently we don't care, right? Let's try to get everything.
What I mean is these two solutions, they are symmetric.
Correct.
Yeah.
True. That is true.
So is that possible? We just get one, then we ignore another one.
I mean, you can do that. You can
Okay.
do that, but typically it is more complicated when n increases.
Yes. Okay.
Right? To eliminate duplicates, that's more complicated.
Okay.
Okay. Right. When I say duplicates, I meant rotational, variants. Okay. Now let's look at the code here. So let me show you the diagram first. See, it will look like this. Oops. Okay, so see, this is your backtracking algorithm. See, you can try one queen here or here or here or here. See, we are trying to place one queen in row 1, right? In row 1, you can place it in column 1, column 2, column 3, column 4. Then you want, so in our terminology, we will call it as depth 1, right? Depth 1. Then this is depth 2 or row 2. In row 2, you will place the second queen in row 2. So that can be placed either here or here or here or here. In general, the possibilities. However, the constraint says that they cannot clash, so you cannot place here. They cannot clash, so you cannot place here. So the only options for the second place, right, is here or here, given that the first queen is placed at the corner. Make sense? See, the branch factor would have been 4 because there are 4 columns. However, many will be empty, right? Because the constraints will be violated. Make sense? So you see that as you go down the tree, the branch factor keeps reducing. It keeps reducing. And at some point, it will be only 1. Right? So here there can be multiple solutions. See, these are the multiple solutions. The backtracking algorithm covers all these solutions. So this is how we want to cover, right? All, I mean, this makes sense, right? So try all possible combinations for row 1, then all possible combinations for row 2, all possible combinations for row 3. If you look at it, there is no child function here. Why? Because you cannot place here. You cannot place here due to a clash with the second queen. You cannot place here. You cannot place here. So all these child functions, right, are kind of null. Make sense? So this is how, see, once you come to this state, there are no more child functions. At this point, you backtrack. That's the core meaning of backtrack. When you hit the dead end, you cannot go further. There is no other option than to backtrack. That means go to the first position where you came from. Now let's see the code here. See, what is the idea here? So we will use some data structures: column, left diagonal, right diagonal, and all these are initialized to 1. So we have the array of column of 1 to n, and left diagonal 1 to 2n minus 1, and right diagonal 1 to 2n minus 1, and all are initialized to 1. So what is the meaning of this? See, so you have n columns, right? N columns, 1, 2, 3, 4, 5, 6, on up to n. Currently, every column you assume that it is initialized with 1. That means 1 means empty here. When you place a queen, if you place a queen in the 7th column, right, then column of 7 will become 0. Similarly, left diagonal means this, right diagonal means this. The number of diagonals are 2n minus 1. If you look at it, there are 2n minus 1 diagonals in a square. 2n minus 1 left diagonals, 2n minus 1 right diagonals. Again, so all these are initialized to 1. 1 means currently no queens are placed. No queen is placed in this particular diagonal. No queen is placed in another left diagonal, so on. Initially, everything is empty, right? So we place we set it to 1 in all these columns, left diagonal, right. Okay, next. So we will have the solutions in R of 1 to n. So R of I is equal to j means that in the ith row, in the jth column, ith row, jth column, you place a queen, right? In the ith row and the jth column, you place a queen, right? So R of 1 to n will be like our example, the previous example we saw, right? 2, 4, 1, 3. That means first row, second column, right? First row, second column, second row, fourth column, third row, first column, fourth row, third column. So that will be one solution, right? So on. Now, what does this say? If depth is greater than n, then print of R of 1 to depth minus 1. Else, so this is the idea. I is equal to 1 to n, right? And then you have some big constraints. And then you have R of depth is equal to I. Then allocate resources. N queens of depth plus 1, deallocate resources. So let's go one over, like step by step. Let's look at line 3. I is equal to 1 to n. Why do we have it? I is equal to 1 to n. Why do we have it? So there are n columns, right? We want to consider for every row, there are n columns. We will try to cover all columns for every row. Hence, we have I is equal to 1 to n. I means the column number, right? Column number 1, column number 2, so on up to column number n. Okay, so if these constraints are satisfied, that means you can place a queen in the ith column in the depth row, right? We will come to this constraint later, but if this is satisfied, place the queen in the depth row in the ith column. So that's the meaning of R of depth is equal to I. Next, You allocate and deallocate resources. Okay, now we need to understand this as a whole. And deallocate resources is simple, right? So initialized value was 1, you decrease it by 1, so it will be 0. You decrease it by 1, everything will be 0 here. Deallocate means everything will be 1 here. Okay, now we need to understand this constraint. This is the most important. So what is the meaning of this constraint? So this says that it is possible to place a queen in depth row, ith column, right? Now let's look at this matrix. Ith column, depth row. If column of I is equal to 1, what does that mean? If column of I is equal to 1, it means that there is no queen placed in the entire ith column. If column of I is equal to 1, it means that no queen has been placed in the ith column. So there won't be an attack, right? Column-wise attack with the ith queen placed at the ith column. So you can place. I mean, there is no problem with the ith column itself, but we still need to check the diagonals, right? So nobody has kept a queen in the ith column before, hence it is 1. So there is no problem with respect to column. What about left diagonal? Left diagonal. See, this is the left diagonal. So this left diagonal says that left diagonal of n plus depth minus 1. So this says that if okay, how do you get these numbers? We will compute it later. N plus depth minus I is equal to 1. There is no problem with the left diagonal that passes through. So this is the cell, right? The left diagonal that passes through this cell is n plus depth minus I. So this is the left diagonal that passes through this cell, depth comma I. Similarly, the right diagonal that passes through this cell is depth plus I minus 1. Right? So if this is 1, if this is 1, if this is 1, there is no other queen in the same column or in the same left diagonal or in the same right diagonal. So it is a free cell. So you can place the queen at this cell. There won't be any clashes with the previously placed queens, right? That's the meaning of all these 3 constraints, right? Check for the column, check for the left diagonal, check for the right diagonal. Now the only question is, okay, this ith column is very simple, but how did you get n plus depth minus I? How did you get depth plus I minus 1? So let's see a simple example here. So let's take this first. 1, 2, 3, 4 row numbers, 1, 2, 3, 4 column numbers, right? So if you add row plus column numbers, what do you get? 2, 3, 3, 4, 4, 4, 5, 5, 5, 5, 6, 6, 6, 7, 7, 8, right? So depth plus I. Now look at this, depth plus I. Now let's do depth plus I minus 1. What do you get? Minus 1. So you get 1, 2, right? 3, 4, decrement by 1 everywhere. 4, this is 4, 5, 6, 7. So this is your right diagonal, right? The right diagonal passing through a cell is given by depth plus I minus 1. So this is your first right diagonal. This is your second right diagonal, third right diagonal, fourth right diagonal, fifth right diagonal, sixth, seventh. Given any cell, you can find the right diagonal that passes through that particular cell using this formula, depth plus I minus 1 or row plus column minus 1, right? Similarly, try to find the formula or try to apply this formula for a cell. See, if you apply this one, 1, 2, 3, 4, 1, 2, 3, 4, right? So here n is equal to 4. Depth minus I, 1 minus 1, 0. 0 plus 4 is 4, right? And then 2 minus 1, 1. 1 plus 4 is 5. And you will see that, okay, let's do one more example. 2 minus 2, 0 plus 4, 4. You will see that these will be left diagonals. If you compute everything, right, you will see that 3, 3, 3, 2, 2, 1. So these are the left diagonals. So given any cell, you can compute the left diagonal of that particular cell using this. Given any cell, you can find the right diagonal corresponding to that particular cell here. Okay, so that's why we use these terms, and this is how the algorithm works. And you saw the picture, right? Recursion tree before. That's exactly the recursion tree that will be produced, but the pseudocode will be like this. Okay, so these are the 3 problems I wanted to cover in backtracking. So go over the pseudocodes again, go over the recursion trees again, and practice a lot. So if you try to code it and debug it, I think you will try to understand this in a much better way. Okay, so we will stop here, and in the next session we will complete NP problems, or cover some high-level ideas of NP completion.